Hello, Honors Chemistry, and welcome to your Chapter 13 review, where we are going to go ahead and work through a few problems together. So, starting with the first one. So it says that 1.33 grams of sodium iodide are added to some water. What is the concentration of the solution, right? So first, let's pick out some keywords, right? So concentration is clearly our question, right? Our given, what we're looking for. Nope, our goal, what we're looking for. And when we think about concentration, what's concentration really mean? Right. It means molarity, right? It means that I have to find moles, right, per liter. That's what I'm looking for, okay? So, and in this case of the solution, and solution simply means a solute dissolved in a solvent, right? So then we need to read the problem. Oh, sodium iodide, this is my solute, right? And this is going to be, if that's how much water we're adding, right, unless it says otherwise, we can just assume that that's also the volume of my solution, right? And so that's all it is, right? It's a, here's my solute, here's my solution, right? Don't try to make it complicated by writing a reaction for sodium iodide plus water, because that would be wrong and weird and doesn't even make sense because you don't know how to write a reaction for that yet, right? So yeah, don't make life harder than it is. So that means we need to get to moles. So we would do our 1.33 grams of NaI, and we would turn that into moles, right, using its molar mass. And then we would simply divide by my volume, which is that, right? And then my liters my liters don't cancel because that would be problematic if it did. But our grams of NaI cancel. Our remaining unit is moles per liter. Yes, and that's going to give us the answer to that one. Good? All right. Next one says, what mass of silver nitrate, so that's that part, must be dissolved in this much water to make 0.1 molar solution. So first of all, this is our question. How many grams of silver nitrate? And this is a piece of information that you might be tempted to say is a given, but you would stop and rewrite this as moles of solute. So that would be our AgNO3 is equal to 1 liter of our AgNO3 solution, right? Which means conversion factor not given. That is our given, and we just want to know how much silver nitrate to use, right? So we're going to take our 0.01 liters of our AgNO3 solution, and we're going to use our molarity to get to moles. So for every 1 liter of my solution, I have 0.1 moles of AgNO3. Now I just need to use the molar mass of AgNO3. Per 1 mole. And if I look at my units, we'll see that we have solved for the grams of AgNO3 necessary to make 100 mils of 0.1 molar solution. Yes? All right. Next up, it says we've got this volume of that concentration hydrochloric acid, our diluted new volume. What is the new concentration? And again, new concentration means new molarity, right? We've got keywords in here like diluted. So what are we supposed to do here? Right, this is simply an M1V1 equals M2V2, right? Where we will, and again, your units need to match on either side. So we will take our 8.3 milliliters times our 12 molar. So basically this is we're going to take 8.3 milliliters of our stock solution, of our concentrated solution, and we want to know if we dilute that down up to 100 milliliters, what is going to be our new concentration, yes? Meaning we're adding 92-ish mils of water, and what new concentration are we going to end up with, right? And so then we would solve for that. What I would strongly recommend is that you don't try to put M2 on the right. No, on the left. I know a lot of times people want to move the variable to the left side of that equal sign, but don't move it, right? If you move it, sometimes you do weird things that you shouldn't do, right? So just leave everything where it is. 8.3 times 12 divided by 100 gives you M2. Good? All right, next up. Here it says 20.5 millimeters cubed of solid aluminum are added to this much aqueous copper 2 chloride. what color is the aqueous solution at the end of the reaction? So here, keyword, end of the reaction, right? In addition, I'm talking about some aluminum and I'm talking about some copper chloride, right? So now, different from the previous ones, here I'm just talking about a solution, right? So if we're looking at our wording, here we're talking about a solution and we're talking about the stuff that make the solute in that solution. Here we're talking about, again, the solute of the solution, right? Or we're talking about a dilution where all we're doing is adding water, right? Now we're talking about two different chemical substances being mixed together, which is Q, write a balanced equation. So we'll start there. We have some aluminum solid plus some aqueous copper 2 chloride. And then we would look at this and say, ooh, element plus ionic compound. Switch the element with the thing it's most similar to. Aluminum is more similar to copper. They're both metals. So we're going to end up with AlCl3, aqueous based on our solubility rules, and some copper solid because it's a metal. And then we would go back and balance. And we would be done with that part. Now, it says I would like to know the color of the solution at the end. What's that really code for? Right, I want to know what it looks like when it's done, because what it looks like is going to be based on, correct, what reactant was limiting, what reactant was excess, because going back to things that we know, right, we know that copper chloride, aqueous copper chloride, is blue, right? We know that solid copper is brownish red, right? Aluminum chloride aqueous is going to be clear and colorless, right? And we know what aluminum looks like. So these are all things we know. So if I want to talk about what anything looks like at the end, really that's a veiled way of saying what's limiting and what's excess. So if we look up, yep, indeed, we have another clue because we know the amounts of both reactants. So that's your other ding, ding, ding moment. Find a limiting reactant. Even if you didn't know what else to do, even if you didn't understand how to deduce the color at the end, you know the amounts of both reactants, figure out a limiting. And that's going to get you a bunch of points just for doing that, okay? So let's start there. So we have 20.5 millimeters cubed of our aluminum. Millimeters cubed is a measure of, correct, volume. So we're going to have to get to centimeters cubed so we can use that. So thinking all the way back, we've got 10 millimeters is equal to 1 centimeter, but then they need to be cubed, so we'll do that. And then, now that we're at centimeters cubed, we know that there are 2.70 grams of aluminum for every 1 centimeter cubed of aluminum. I also know that there are 26.98 grams of aluminum for every 1 mole of aluminum. And I know that for every 2 moles of aluminum, let's pick something. Let's go with 3 moles of copper. And I'm just going to leave it in moles of copper because I just need to know which is limiting. I don't need to know how much of any given product is made. So I'm just going to stop there. And let's go ahead and set up the next part, which says 20.5 mils, so 0.0205 liters of my CuCl2 aqueous. And then I'm going to use the molarity, so 0.25 moles of my solute for every 1 liter of my solution. And now I'm going to go from my CuCl2 to my copper, right? And now we just need to figure out which one of these is limiting. Okay, and so now if we take a look at our numbers, right, we can see that this is the maximum amount we can make, which means that this is our limiting reactant. So if aluminum is limiting, right, if I want to know what color the aqueous solution is at the end, I'm going to have excess this. So at the end, my aqueous solution is going to be blue, right, because I'm still going to have some copper chloride in there, aqueous copper chloride, right? Other observations that would be pertinent at the end would be that there would be no more silver solid, right, or no more gray solid remaining because that was our limiting reactant, right? The only solid left in the beaker would be the brownish red newly formed copper, right? Does that make sense, right? These are observations that we can put together based on what we know, right, from the math. All right, next up, what volume, right, of this solution is needed to neutralize this, right? So first of all, looking for clues, right? You might see volumes and molarities, and you might want to do M1V1 equals M2V2. But then you'll say, oh, keyword, neutralize. That's a type of chemical reaction. And this is talking about sulfuric acid. This is talking about barium hydroxide. Must have a balanced equation, right? So barium hydroxide, aqueous with my sulfuric acid, aqueous is going to produce some barium sulfate because we're going to switch our cations. This is going to be solid actually. And my H2O, 2 of those, and we would be done, right? And so this is a conversion factor, not a given, and it converts between moles and liters of barium hydroxide. So I'm going to need that when I'm ready to get to volume, but that means I'm going to start over here. So I'm going to start from my 750, oh, look at that unit, microliters of H2SO4. So I'm going to have to get out of microliters to liters, so you have to think all the way back, right? And we're going to end up there, and then we're going to go from use our molarity, which says that there are 0.5 moles of sulfuric acid for every 1 liter of our sulfuric acid. And then we're going to go 1 mole of sulfuric acid, that says 2, to 1 mole of barium hydroxide. And then we're going to use our molarity, which says that there are 0.5 moles of barium hydroxide in every 1 liter of our barium hydroxide, right? And so that, right, is going to give us the amount of barium hydroxide that's going to exactly neutralize that amount of sulfuric acid. Yes, does that make sense? And it should be a small number because we're starting from microliters, which is a very small amount. Yes? All right. Thank you for listening. Be good, study, and I will see you soon. Bye.